Alright, in this video we're going to be discussing example 9.17 from the free online introductory statistics textbook, which you can download via this link here. Okay, so this is a hypothesis test for a proportion, and we have the not equal alternative hypothesis, though I will briefly talk about how it's different when you have a greater than or less than alternative hypothesis. Okay, so let's start by reading through our example. All right, so June believes that 50% of first-time brides, so let me go ahead and highlight that 50% of first-time brides in the United States are younger than their grooms. Okay, so half are younger and half aren't. That's her belief, okay? She performs a hypothesis test to determine if this percentage is the same or different than 50%. All right, so the same or different than 50%. Joan samples 100 first-time brides, and 53 of that 100 are younger than their grooms. I want to do a hypothesis test with the 1% level of significance. All right, so first thing, we need to recognize that we are testing a proportion, right? Notice we're talking about 50%, right? We're not talking about the average of something, right? So first thing you have to notice, is this a hypothesis test for proportion or is it a hypothesis test for average? And since we're talking about a percentage, it's a hypothesis test for a proportion, okay? Once you've noticed that you're talking about a hypothesis test for proportion, you need to know, is n times p greater than 5, and is n times q greater than 5? You must test this before you can move on with a hypothesis test for a proportion. And if this is not met, then basically you need other methods to do this hypothesis test. You can't use the standard method that you learn in introductory statistics class where you use the normal distribution. You're not going to be able to use the normal distribution, basically. Okay, so what's n? N is our sample size, 100. What's p? P is going to come from whatever the null hypothesis is. All right, and I'll talk about that a little bit more in a second, but basically it's this 50%. It's whatever you're testing, okay? So we're testing 50%, so 50% is 0.50, okay? Is that greater than 5? Well, 100 times 0.5 is 50, so that checks off. All right, what's Q? Q, in general, Q is 1 minus P. So in this case, P was 0.5, 0.50, 0.5, same thing. So 1 minus 0.5 is also 0.5, okay? So n is 100, that's the number of people we've sampled. Q is 0.5, or 0.50, same thing. Greater than 5, again, this comes to 50 greater than 5, which is true, okay? So once you've tested that assumption, you can move forward. All right, step 1 in all hypothesis tests, step 1 in all hypothesis testing is to write your hypothesis, all right? So write out our null and alternative hypothesis. Your null hypothesis, right? First off, what are we writing a hypothesis for? We're writing it for P. So you start with P. If you're writing it for a mean, you would have started with mu, right? So the population proportion, or P, because we're talking about a percentage, right? All right, the null hypothesis will always have the equal sign. All right, always. Null hypothesis, that is what we are assuming to be true, so it always has the equality. Okay, now the alternative hypothesis, because we're trying to test whether or not it's the same or different than 50%, so the same or different than 50%, that's why the alternative hypothesis is not equal. Okay, and then 0.5, because we're trying to test whether or not it's equal to 50% or not. So always change that percentage over to a decimal. So 0.5 or 0.50, same thing. All right, so the same or different. Same or different, that's that not equal to. Okay, if it was, we're trying to test if more than 50%, if we're trying to test whether or not more than 50% of brides are younger than their grooms, then we would have had the more than symbol. If we were trying to test whether or not less than 50% of brides are younger than their grooms, then we would have had the less than symbol. All right, but the null hypothesis, the first hypothesis, this one, HO, the null hypothesis always has this equality. The alternative is what gets the not equal or greater than or less than. Okay. That's step 1. Step 2 in all hypothesis testing is to now calculate your z-statistic, your test statistic. Sometimes you'll see that written as z subscript ts, test statistic, or just subscript t. Okay. For proportion, the formula is p minus, or p hat minus p divided by the square root of p times q divided by n. Okay, so now I just need to identify what each of these things are. So what is p hat? Let's start with what is p hat. What is p hat? P hat is your sample proportion. Okay, so let's go back and read through the question. What is our sample proportion of brides that are younger than their grooms? Well, here we go. Here's the sample. Oops. So Joan samples 100 first-time brides, and 53 of them are younger than their grooms. So out of the 100, there's 53 that are younger than their grooms. So the sample proportion is 53 over that 100, or 0.53. Okay. So let me write this down here. So we have 0.53 minus, what's p? This p here, this p in this formula right here, this p will always come from the null hypothesis. It comes from our assumption. That's why the null hypothesis has to have the equal sign. P equals 0.5. All right, so 0.5. Okay, notice that in the denominator, this is P and Q. There's no hat on them. So again, we're getting it from the null hypothesis, 0.5. Okay, what's Q? 1 minus 0.5, which is also 0.5. Okay, and then what is N? N is our sample size, 100. All right, and you can pull out your calculator and figure out what this is. I like to pull out Excel as my calculator. All right, nice thing about writing it in Excel is if I'm solving multiple of these type of problems, I can just use formulas to make it nice and easy to figure this out for lots of different problems at the same time. Okay, so p hat is that, let's see, 53 divided by 100, or I could have just written 0.53. P is 0.5. Q is equal to 1 minus this cell, okay? 1 minus B2, whatever P is. There's also just 0.5. I could have just typed in 0.5. N is 100, okay? So let's calculate our Z subscript T, our test statistic. Okay, so in the numerator, so let me use parentheses to indicate I'm in the numerator. I have P hat, so I'll just put that cell there, minus P, okay? Close those parentheses, divided by SQRT, the square root, of P times Q divided by, okay, looks like my cells are overlapping. I can't press this one, so let me just type in, what's that, B4? B4, okay? And I get 0.6. Okay, so there's my test statistic, 0.6. So then later, if I were to, collect a different sample, 55 over 100 or something like that, the test statistic will automatically update. That's why it's nice to use Excel. Okay. So 53. Okay, so I have 0.6 as my test statistic. All right, so let me write 0.6. All right. So now once I have this, step 3 is to calculate your p-value. All right, so we need to figure out what our p-value is. Okay, the way we calculate our p-value has a lot to do with the way our null and alternative hypotheses are written. Okay, so in a two-sided test, which this is a two-sided test, whenever you have that not equal in the alternative, you have a two-sided test. Okay, so when I draw out my normal distribution, here's 0. 0.6 is somewhere above 0. 0.6. And what I want to know is the probability of observing a test statistic that is that extreme. So it's a 0.6 or it's more extreme. Okay. And since it's a two-sided test, I will also want to consider the negative 0.6 option. So it could be above 0.6 or below negative 0.6. And that's basically the not equal two-sided test p-value. Okay. But notice that because this is a symmetric distribution, what I find here over here that I'm marking now in blue is exactly the same as what's over here because this is a symmetric distribution. The normal distribution is symmetric. Okay, so if I find one of these areas, then I can just multiply it by 2. So how do we find, in general, the probability that z, right, so this is a standard normal distribution, is less than less than negative 0.6 because that's easier. I can use Excel really quickly to figure this out. So the probability that z is less than negative 0.6 will be this area here, right? Less than negative 0.6. So let's go to Excel and figure out what that is. So next I need to figure out the probability that z is less than 0.6, negative 0.6, equals norm dot s, that's for the standard normal distribution, dot dist, open parentheses. Okay, the z value is that negative 0.6. Okay, so if you're doing a two-sided test, always give it the negative one because that's the less than over here, right? If I give it the positive 0.6, then it would find all of this area back here, which includes the area, this black area that I don't want it to include, right? So I'm going to give it the negative 0.6 to be just this red area here. And then always true for cumulative. That just means you're finding the probability or less than. Press enter, and there we go, 0.27. Okay, so what's my p-value? So p-value will need to be that red area and then also this area over here. So I need both tails, two-sided test. So I'm going to need to take that and multiply it by 2. So there we go. My p-value is 0.5. I'll round it to 2 decimal places, 0.55. That 8 takes the 4 up. So what's my p-value? My p-value is 0.55. Okay. All right. Okay, so that's because we found this area, this red area is 0.27, and then this blue area is also 0.27, so multiply 0.27 by 2, and that's how you got 0.55, right? And there's some rounding there. Okay. All right, lastly, we need to make our conclusion. Okay, we need to make a conclusion based off of this. So are we going to accept the null hypothesis? Are we going to reject the null hypothesis? So that's our two choices. We want to either reject this null hypothesis, reject it, say, that seems unrealistic, right? And if we reject the null hypothesis, that means that we basically say no, and we're in favor of the alternative, right? So the alternative seems realistic. So we reject the null hypothesis, or we fail to reject the null hypothesis, in which case we're like, maybe not so much for the alternative. Okay? So those are our two choices. Do we reject HO, or do we fail to reject HO? Okay, those are our two choices. And how do we make this decision? In general, we reject the null hypothesis when our test statistic value, this test statistic value, 0.6 in this case, is extreme, right? If it's really extreme, then maybe that test statistic actually doesn't come from this distribution, right? So if it's extreme, if we have an extreme test statistic value, that means that this area, right, this area here, this p-value area is really small. So we reject the null hypothesis when the p-value is small. How small? When the p-value is less than alpha. Okay, and what is alpha? Let's go back up top. For this hypothesis, she uses a 1% level of significance. That is alpha. Alpha, 0.01. Okay, why did I say 0.01? Because we have to change that percentage into a decimal. So remember, you move your decimal over twice. So 1% equals 0.01. Okay, so change the percentage over to a decimal. Okay. So if the p-value is less than alpha, we reject the null hypothesis. However, we fail to reject the null hypothesis in general if the p-value is more than alpha. Okay, so you have those two choices. And let's see, in this scenario, our alpha is 0.01. What's our p-value? We just calculated it. We just calculated it. It is 0.55. Now, 0.55 is much larger than 0.01. So we are in this scenario where 0.55 is larger than 0.01. So the decision that we're going to make is we're going to fail to reject the null hypothesis. We're going to say, hey, you know what? It looks like that 0.6, that is a reasonable, that's not really an extreme value. So it's reasonable that when we made this assumption that p equals 0.5, that's a reasonable assumption. Okay? So if this is a reasonable assumption, we are going to fail to reject the null hypothesis, which means that, hey, you know what? There's not really a lot of evidence that suggests that the alternative is true. Okay? So let me go ahead and write that down. So we write our final conclusion first in terms of the null hypothesis, and then lastly, last step, we write our conclusion with regards to the alternative. So since we have failed to reject the null hypothesis, that means that there is not enough evidence to suggest that the proportion of first time brides in US that are younger than their grooms is different than 50 or 0.5, right? 50% or 0.5, right? So since I've failed to reject the null hypothesis, there's not enough evidence, right, that the proportion of grooms is different Different than. Remember, different than is what the alternative hypothesis is. The alternative hypothesis was that P is not equal to 0.5. Okay? And if I had rejected the null hypothesis, the way I've written this step number 5, it would have been exactly the same. Had I rejected the null hypothesis, I would have written this exactly the same, except I would have gotten rid of the word not. I would have said there is enough evidence to suggest that the proportion of first-time brides in the U.S. that are younger than their grooms is different than 50%. Okay? All right, one last thing I want to mention. This is a two-sided test. However, if my alternative hypothesis, so if my null, say I still had the same null, P equal to 0.5, and my alternative, right, H1 or HA, sometimes you'll see it with an A, same thing. If my alternative was P greater than 0.5, the only thing that would be different is the way I calculate my p-value, okay? If I had greater than 0.5, then I would only be concerned about the greater than side of 0.6, okay? So when I calculated my p-value, I would have needed to know only what is in this tail, right? Which I think we calculated in both tails, there was like about 0.27, so the p-value would have been 0.27 if it was a one-sided test.